Hello, I'm Jan Vincent Triambilio and I will explain our laboratory activity 3, Digital Signal Time Transformation. The main objective of this activity is to understand the concept of time transformations in digital signals, including time shifting, time scaling, and time reversal. Through this experiment, we also aim to apply Python programming to visualize these transformations and analyze how they affect discrete time signals. In digital signal processing, these operations are very important because they are commonly used in systems like telecommunications, radar, biomedical analysis, and even disaster warning systems. To begin, I created a simple digital signal where x of n equals 1, 2, 3, 4, 5 for n equals 0 to 4. This signal serves as our original reference. I first plotted it using matplotlib stem function to show that the signal is discrete and defined only at specific points. Then I performed the three main transformations. The first one is time shifting, which moves the signal along the time axis without changing its shape or amplitude. By adding 2 to n, I delay the signal, shifting it to the right, represented as x n minus 2. By subtracting 2 from n, I advance the signal to the left, represented as the x n plus 2. The plot clearly shows how the entire waveform moves earlier or later in time depending on the direction of the shift. Next, I applied the time reversal, which flips the signal about the vertical or time zero axis. This means that the what was originally at positive n is now at negative n. In the plot, we can see the reverse signal x negative n mirrors the original xn. This transformation is very useful in analyzing symmetry. If the signal is even, the reverse version looks the same. If it's odd, it appears inverted. Time reversal helps in understanding how signals behave when mirrored in time. Finally, I demonstrated time scaling, which involves compressing or expanding the signal in time. For expansion, I multiplied n by 2, which stretches the signal apart, make it appear slower in the time domain. For compression, I divided n by 2 using integer division, which brings the samples closer together, making it look faster. The resulting plots clearly show how scaling changes the spacing between data points but does not affect the signal's amplitude or shape. From this activity, we can observe that the time shifting moves the signal with altering its structure. Time reversal flips it around the vertical axis, and time scaling adjusts how spread out or compressed the signal appears. These transformations are very useful in real-world applications, such as adjusting delays in communication systems, reversing data for analysis, or controlling playback speed in audio and video processing. In conclusion, this laboratory activity helped me understand how digital signals behave under different time transformations. Using Python, specifically NumPy and Matplotlib, made it easier to visualize these operations clearly. I learned that time shifting, scaling, and reversal are essential tools in digital signals processing because they allow us to control when and how a signal occurs without changing its fundamental properties. Overall, this experiment improved my understanding of signal manipulation, which is vital in designing and analyzing digital systems effectively.